One of the mathematical theory that we're going to need a little bit into the finite volume method is actually Gauss divergence theorem. And you should go back and review the vector calculus to understand what the Gauss divergence theorem is about and how to use it to find some important calculation parameters. The statement of Gauss divergence theorem, I'm going to go quickly here, is the flux of a vector field F. So if we have a vector field F, the flux of that vector field through a closed surface equal the integral of the divergence of that vector field over the volume. So let's assume that we have a domain like this. This is a three-dimensional domain here, so it has a volume and it has surface area. And let's assume we're talking about a heat that's presented by a vector field coming over that control volume. So if you want to understand the change of the thermal energy inside the volume of that control volume, you can get that by getting the information about the flux that's crossing the surface of that domain. Again, the change of the energy content, I'm giving energy as an example here, the time change, or the change of the energy content within that control volume can be calculated by knowing the flux crossing the boundary or the outer surface of that domain. So from whatever is crossing the outer surface, you can determine what happened to the internal content of that volume. That's simply the interpretation of that Gauss divergence theorem. Mathematically, it states that the double integration of a vector field F dot n over the surface, and we usually have here S, mean that this is double integration over the surface. That's area integration, right? Or integration over a surface should equal to the triple integral, that's the volume, right, of the diversion of that vector field F over the volume of that control element or control volume. So whatever is happening inside the volume can be calculated by whatever is crossing the surface of that volume. Why that's true? That's a question. Why the vector that's crossing? By the way, the vector could be a heat, could be a velocity, could be any one of the parameters as a thermal hydraulics team is interested in. Why it's what's happening inside the volume is only expressed or can be expressed by what's crossing the surface of that domain. So let me draw that domain again here, and let's assume that we're gonna divide that domain, we're gonna mesh it, and we're gonna divide that domain into cells. And let's talk about, for example, the thermal energy. Let's assume that, okay, for this cell here, we will have a kind of velocity vector or heat transfer into that direction and into that direction, into that direction, into that direction. That's an internal cell, and we're looking for the divergence or the flow of thermal energy. Could be going out, could be coming in, doesn't matter. But if I look to this cell and the neighboring cells, what you're going to notice here, you always have a canceling vectors internally. So this vector will cancel this vector. This vector will cancel this vector. This one will cancel this one. They are against each other, right? So what you're going to end up with, if you go any one of these boundary cells, this will be met by another one in here. This will be met by an opposite vector here. The only one that's going to lift is the one that's going out from that cell to the outer surface. So you will find yourself that only what's happening inside will cancel out, and any change for the internal or inside that control volume can be expressed by what is just going through the surface of that domain because of that internal cancellation of these kind of vectors inside that domain. I hope that, guys, just give you some presentation for that theory here. Always the internal vectors are canceled out because they are against each other. What's going to remain is only the component of that vector that's leaving the surface of that domain. That's why what's happening inside is reflected at the surface of that domain. That's the just a way to present that stuff. So now, for those who doesn't remember, what's a vector field? What is a vector field? F. Actually, vector field is a method or a way to graphically represent any vector. So it's a graphical method to present a vector. And since we are dealing with velocity, and velocity is always a vector, so that's what we need from a vector field. So for example, let's assume that example. I told you that I have a velocity vector that's function of x and y, and it has two components given by x squared and 2y. How are you going to visualize that velocity vector? How you can visualize? How you can tell me, oh, that fluid is going this way, that fluid is going this way, that fluid is going this way. And it depends on the coordinate of your domain, right? So to do that, for example, we construct the xy domain. Here's x and y. And we pick a point. Let's assume that we're going to pick a point 1 and 1, which means that at 1 and 1, you substitute your velocity vector at this coordinate is going to be 1 and 2. So I will go into point 1 and 1. This is where I am here. That's 1 and 1. Then I will pick point 1 and 2. It's here. I'm going to connect a vector. It is telling me that at point 1 and 1, your fluid is going vertically. What about if I choose -1, -1? I'm picking random numbers here. So the velocity vector should be 1 as a value, -1 squared, that's 1, and -2. So I have -1, -1, that's somewhere in here. And I go for 1 and -2, that's somewhere in here. I'm going to connect that arrow here, and that's going to give me the direction of the flow. Then you notice that, and I'm not going to continue substitution here, but sometimes you see vectors like this, which may be telling you, hey, I have a fluid that's circulating around the x coordinate or 0, the origin coordinate. Or maybe after you pass this, the velocity vectors is all the way going up. So I have a circulation to a certain distance, then the fluid go vertically after that based on that vector. This is what we call the vector field. It's a graphical representation of any other vector. And I'm sure you guys have seen that a lot in physics and fluid mechanics course as well. So that's the definition of the vector field F. What is N? N is actually a normal vector. to the surface. It's the normal unit vector to the surface. So if you pick up any piece here and you draw a unit vector that's normal to that surface, that's the vector n here. Okay, so why we need that unit vector n normal to the surface? Because if you go back to the vector calculus as well, you will find that f dot n is simply the normal component of vector f to the surface. What does that mean? Let's assume that our surface is that rectangular here, and you have a velocity vector that's going this way, that's going this way, and this is going this way, and this is going this way. This is my velocity vector for each face of that control volume. All I'm interested in, that velocity here has two components, horizontal component and vertical component. This is v dot n component. So we are always looking for the vertical component that's perpendicular to the surface to quantify our flux actually. According to the divergence theorem, we're looking to the normal component over that surface to integrate. That's why f dot n will give me that vertical component of that vector over the entire surface here. So that's the mathematical representation of f dot n. Okay, that's the component that's normal to the surface. So we can use that in the divergence theorem. I think I would like to go quickly through an example. It could be a nice example to deal with. So let's assume that you have a cubicle, just to show you the importance of using the divergence theorem. So let's assume that we have a cubical shape here, example. So the statement of the example is you are given a vector field F is given by 2xz, comma, minus y cubed, comma, yz, and we would like to calculate the flux across the boundary or the boundaries of unit cube. So we have, let me draw the cube first. That's my unit cube. Okay, so each side length is unity. Let's set up the x direction. That's my x direction. That's my y direction. I'm gonna call that my z direction. And it's each side has unity here. And we have that vector field that's crossing that cubical shape. It could be crossing because it's generated internally, or it could be like heat generation, or it could be actually a heat that's going over that cubical shape. And we would like to know how much of that energy will cross all the faces, the boundaries of this cube. In this case, we have to break down each one of these faces separately, and we deal with it like this case here. So let's assume we will pick up the, that's my face one. I will pick up that face here. I will call that face one. So this is face one, that located at a distance here, that's 1. And the area here is 1 and 1. Remember, this is unit cube here. Step number 1, define the normal vector. My normal vector will be, let me get a different color here. The normal vector will be like this. That's my n vector, right? So the magnitude is 1 and the direction is in the x direction. So my n vector is actually 1i. The magnitude is 1 and it is going in the x direction, and it has 0j and 0k. That's if I want to write this in a vector form, right? So it's actually 1i, 0j, 0k. That's my n vector. So to calculate the flux, first let's get actually f dot n, right? That's the normal component. That's the normal component to that phase. So this would be simply 2xz, comma, minus y cube, comma, yz, dot 1, 0, 0. You will end up having the normal component of that vector field is simply 2xz. To get the flux, you have to do the double integral over the surface of that f dot n, right? ds, whereas ds is the surface area, right? Or the element surface area. So what's my ds? What is the surface area of that element here? This is dy, this is dy, right? And the height is dz. So ds of that phase is simply dy dz. So if I want to get that integration, it will be integration of f dot n, which is 2xz. I'm going to integrate that twice, dy dz, and the y change from 0 to 1, and the z is it changed from 0 to 1. So it doesn't matter the order. So 2xz, you integrate relative to the y, it's going to be 2xyz. Remember, you have from 0 to 1, and whatever is coming out will be reintegrated again relative to the z. So if you substitute for y equal 1, that's going to give me 2xz. If you put 0 minus 0, so that bracket here will be 2xz. So I'm going to integrate from 0 to 1, 2xz, right? dz. So this will be 2x is constant. Z is going to be z squared over 2. I'm going from 0 to 1. So if I put 1, this will be 2 will be canceled out. So it's going to be xz squared. So it's going to be xz squared, which is 1 minus 0. So it's going to be x. And for that phase, what is the x coordinate of that phase? Is 1. X is equal 1. That's the x coordinate of that phase. So the flux from that phase has a value of 1. The flux on that phase has a value of 1. Let's do the backward phase, the phase in the back. So in the back, I will have a normal vector. It's going this way. It's going backward against this one, right? And this is still dy. This is still dz. But the x coordinate of that surface is 0. X is 0, right? That face in the back, the green one here, has a coordinate x equals 0. And the ds, the area is dy dz, right? So let's do that slowly here. So for phase 2, phase 2 is the backward one here. What is the normal vector? It's going to be -1 in the I direction. This is going outward. Keep in mind, n is always an outward vector, right? Normal to the surface. And it has the scale of unity here. So n is -1 in the j, right? 0 in the y, 0 in the z. That's my normal vector. So if I want to get f dot n, will be 2xz comma, minus y cube, comma, yz, dot product, minus 1, 0, 0. I'm going to end up having minus 2xz. So what I need to do is to integrate over the surface f dot n ds. So I want to integrate. ds is the area of that face, which is still dy dz. Each one is changed from 0 to 1 to 0 to 1. F dot n is minus 2xz. But remember, the x coordinate of that back face, x is equal to 0, which means that this integration is already equal to 0. Right? So that's the flux. So this is a flux from phase 1. This is a flux from phase 2. Let's take that face here, just a different one. I will go for phase 3. I will pick up this face here. You draw the normal vector. So n, in this case, will be 0 in the I direction. N will be 0 in the I direction, will be 1 in the Y or J direction, will be 0 in the Z. Vector F, it's still 2xz, comma, minus y cube, comma, yz. So I'm going to get f dot n. That's going to be 2xz, comma, minus y cube, comma, yz, dot product of 0, 1, and 0. This will give me minus y cube. Remember, dot product give you a scalar, right? So f dot n, it's minus y cube. Then I would like to do, to get the flux, I'm going to take the double integration. Now, what is ds for that face? The area of that face is dx times dz. So I have dx dz. I'm still within the cubical shape unit cube here. So I'm going to change from 0 to 1 to 0, 1. Then I want to integrate that minus y cube. Remember, the y coordinate of that face is 1. Y is equal 1. So as if I'm doing integration from 0 to 1, 0 to 1, to minus 1 dx dz. You perform the integration first, you're going to get integration from 0 to 1. You integrate minus 1 to dx is going to be minus x from 0 to 1. Then whatever comes out will be integrated again. This will give me minus 1. You integrate again, it's going to give me minus z. From 0 to 1, I'm going to get minus 1. So the flux from that face is minus 1. Phase 4 in the back, right? Phase 4. The normal vector will be 0, minus 1, 0. 0 in the I, minus 1 in the J, and 0 in the K. But the Y coordinate for that one is 0. So you end up having phase 4 actually has a flux of value equal 0. You try by yourself, you'll find the same. The same will apply for phase 6 here. I'm going to call that phase 6. You will get also for phase 6. Or let's call that phase 5 to move in an order. Phase 5 will also have a 0 flux because of the coordinate of this phase here. Let's see the upper phase here. I'm going to call that phase 6. And let's see what the flux. So we got so far phase 1, it got me a flux value of 1. Phase 2 give me a value of 0. Phase 3 give me a value of minus 1. Phase 4 give me a value of 0. Phase 5 give me also a value of 0. Now the last one is the upper phase here. That's phase 6. The normal vector will be 0, 0, and 1. Right? That's the normal vector. So if I want to get f dot n for phase 6, I will integrate double integral of f dot n 2xz comma minus y cube comma yz dot 0 0 1. Then you're going to integrate all of that ds. The surface area of that face is dx dy. This is the area here. Remember, the z coordinate of this guy is 1. And x and y, both of them are changing from 0 to 1. What is the dot product results? It's going to be yz. You're going to integrate that from dx respect to dx dy. Z coordinate is 1, so that's the double integral of simply y dx dy, right? So this will give me, I will integrate relative to the x first, so I'm going to get yx from 0 to 1, and whatever comes out will be reintegrated dy. You put x equal 1, that's going to give you y, so it's going to be y squared over 2. From 0 to 1, I'm going to get half. So for phase 6, I got the flux of a value of half. So now, if you want to get the net flux, it's going to be 1 plus 0 plus minus 1 plus 0 plus 0 plus half. The final value is half. That's the net flux coming out or getting in normally to the 6 faces of a unit cube. So you can figure out how hard when you are using the double integral to get the net flux out of this cubical shape. Now, how the divergence theorem is making everything much easier now, because simply if you go for the divergence theorem, it states that the double integral over the surface for f dot n ds can be simply done by the triple integral of the divergence of that vector field over the volume of that cubical shape. This is the divergence theorem. Let's see how quick and easy I will get the same answer if I use the divergence theorem here. So the vector field f is given by 2xz minus y cubed comma yz. We would like to use the divergence theorem, so I want to get the triple integral over the volume of that cubical unit cube for the divergence of that vector f dv. Now dv, that's the volume of that element, which is going to be dx dy dz. That's the volume. And the nabla, or the diversion of that vector, will be simply you differentiate each term. The first one relative to the x, relative to the y, relative to the z. I'm going to get 2z minus 3 y squared plus y. So I differentiated the first term relative to the x, so I got 2z. This is relative to the y, I got minus 3y squared. This is relative to the z, so the y is constant, so it comes here. Then I'm going to integrate that from 0 to 1, 0 to 1, 0 to 1. Again, the order is not really important here. So I will start first by integrating that relative to the z. It's much easier. So I will integrate from 0 to 1, 2z minus 3y squared plus y. I'm going to integrate that term relative to the z. What are you going to get? I'm going to get 2z squared over 2 plus minus 3y squared z plus yz. I want to substitute from 0 to 1. 2 will cancel out. You put z equal 1, so it's going to be 1 minus 3y squared plus y minus, you put z equals 0. This term goes away. This goes away. This goes away. So I'm going to end up having 1 minus 3y squared plus y. Then I'm going to integrate from 0 to 1 to the 1 minus 3y squared plus y dy. So you integrate, you're going to get y plus or minus 3y cubed over 3 plus y from 0 to 1. 3 will cancel out. So if you put y equal 1, that's going to be 1 minus 1 plus 1. Minus, you put y equals 0, it's going to come to be 0. This will give me simply 1. Correct? That's when you integrate that, that's going to be y squared over 2. I'm integrating y, so it's going to be y squared over 2 from 0 to 1. So I'm going to get half here. This will give me half. Then I will take integration from 0 to 1, half dx. This will give me half x from 0 to 1. I got half. So the double integral from 0 to 1, 0 to 1, 0 to 1 to the divergence of that vector field give me a value of half, which is exactly the same answer we got after breaking down the cube into 6 faces, and we added up the flux from each one of them. So really, the divergence theorem is very easy to use. You do just one step of integration, you got your results. Instead of breaking your control volume into faces and do the double integral to get the net flux for each phase, then you add up the component. That's how important and easy to use the divergence theorem to get the whatever is happening inside the control volume by calculating what's happening at the faces or the boundaries of that control volume. And that's simply to conclude the divergence theorem here.